So let's go ahead and we'll get started with the next example. So we can actually utilize this to figure out pH. Like I said, you can do this in an in vitro or in vivo setting. And so I've got some examples here and that we're going to work together. And sometimes the hardest part is determining what is the conjugate acid and what is the conjugate base. So here we have calculate the pH of a solution that's obtained by adding so many moles of that Na2HPO4, which unfortunately those are supposed to be subscripts, but they didn't transfer over in the computer program, and 0.1 mole of NaH2PO4. Okay, to make pure water with a final volume of 100 mils, the pKa of the H2PO4 minus is 7.2. So once again, I'm going to just write out what this is. So what that's saying is we have 0.063 moles of, and this time I'm going to put it correctly, Na2HPO4. Okay, and they have 0.100 moles of NaH2PO4. So the hardest part here really is getting, and we're going to stick this into the Henderson-Hasselbalch equation, and we can actually figure out, here they're wanting to know the pH, but we could also work backwards. If you knew the pH, you can figure out the pKa. Or if you know, as long as you know 3 of the 4 variables, you can figure out the 4th. Okay. So, let me see if this will. Oh, whoops. That eraser is really, really big. They're not joking. NaH2. Just trying to write that a little bit more neatly. That's a PO4. Okay, so the question here is which of these is HA and which is H minus. So to remember, this is the Henderson-Hasselbalch equation. The Henderson-Hasselbalch was pH is equal to pKa plus the log of the base form, which is A minus the base, or is HA the base? A minus. So, and these are concentrations, but I'm just going to write it this way. A minus or HA. So the question is, the moiety, the sodium moiety on the top, the Na2HPO4, is that the A minus form or is that the HA form? That's the A minus. And the way it's actually not difficult is just to see which one has the most hydrogens attached is the HA form. And so that's why this is A minus. This one is HA. Now notice when we do concentrations, normally these are moles per liter, and you can still figure out concentration moles per liter. However, and you don't have to write this down, since the volume is not changing here, it doesn't really matter how many liters you have. It's just the ratio. And the reason why I mean that is if we write that out, so we would have moles per liter divided by, and that's of A minus, moles of HA divided by liters. See, the liters cancel out, so it's really just moles over moles. The only time that you have to worry about the volume is if you're changing the volume. If you say, okay, now we're adding stuff and we're subtracting stuff, then you really have to worry about it. But right here, the final volume is still the same regardless, so you don't even have to. But once again, if it helps you, if you get confused, you can always go back, figure out the molarity, and then put it all back into the equation. Okay. So I'm going to just go ahead and put in a blank slide right here. So now we're going to put, and I'll rewrite the Henderson-Hasselbalch for my own personal sanity, because I have been known to accidentally rewrite it wrong, so please let me know if I do that. Now we're just supposed to find pH. pKa was given to us, which is 7.2, plus the log. So for quizzes and exams, you will want to have a calculator. There isn't a lot. That's really ominous sounding, isn't it? There isn't a lot of math necessarily, but there is some math. And so on this first exam in particular, there's going to be there's going to be some math on there. So don't forget your calculator. If you happen to forget your calculator, always work everything out that you possibly can up to show you works, so that way you can get at least partial credit. Just don't put, I forgot my calculator and miss everything. All right, and then we just have the log of the A- form, which I've already forgotten which one was which. The A- form had what, 0.063 over the 0.1. And then it's just plug and chug. So make sure that you do the log base 10, not natural log, whenever you're entering it into your calculator. And I don't have these memorized. So 7.2 plus the log of 0.063.1. And be really careful on long problems. Some people like to do like the log, the division first, and then write it down, and then the log, and write it out, because your errors can add up. And then, before you know it, the rounding error is so big that you've actually changed the answer. This one's relatively small, but it is possible. I have seen it. I get this to be pH 7.0. Now we can, let's just check, see if that makes sense. We have more of the acid form than we have of the base form. There's more HA than A-, so then it makes sense that it's going to be more acidic overall. If you had gone the other way around, then you'd say, okay, I probably flipped something, because it doesn't make sense. You put more acid in and the pH increases, because pH should decrease the more acidic it is. So, but yeah, that's 7.0. All right. Now, in biochemistry, a lot of times we're talking about titration curves. You probably did this a lot in Gen Chem 2 lab. That's why, I mean, it's usually they usually have like weeks upon weeks of doing titration curves. And equivalence points, and all a titration curve is you've taken a buffered system that uses the Henderson-Hasselbalch, and you just look at it as a function of pH, okay? You can see how things change. Equivalence point is just a fancy point at which there is exactly 50-50 percentage, okay? So half of whatever it is, the acid's been neutralized, or half of the base has been neutralized. And so one thing that's not in the notes, oops, here all right, so we can actually make these buffers, acid-base buffers. That's just where you have this weak acid and a weak base. You can alter or vary the concentration of A- to HA, and you can actually make whatever pH solution that you want. Okay, so we do this in vitro, or for many applications, like if you want to make mammalian cell lines or bacterial cell lines, if you want to look at, doing in vitro medicine studies and things like that. But your body also does this. Okay, your body does this in vivo. Does anyone know what's one buffer system in your body? Because what's the pH of your blood, once again, roughly? 7.4. However, what's the pH of the soda? It's really low, and if I drink it, yes, it goes to my stomach first and everything like that. But eventually, the acid from a lot of the soda, from all this, it's going to get entered your bloodstream. You would die. Okay, so what is it in your blood that keeps you? It's a buffered system that uses the Henderson-Hasselbalch equation. Well, it doesn't realize it uses the Henderson-Hasselbalch equation, but it uses that in order to buffer it. So does anyone know what's the buffer system that's used in your blood? Mm-hmm. So everyone take a deep breath. That's it, it's carbon dioxide. So carbon dioxide bicarbonate. Okay, and so that's what it is. And oxygen, that's why it ties into what's called the Bohr Effect. We actually study that later on. To where it's all tied in together, how much oxygen and carbon dioxide to bicarbonate you have. And that combats the pH. Your cells also have a very specific, in the cytoplasm, a very specific a pH as well, okay? It does not use carbon dioxide. Carbon dioxide is not the one that's used. Does anyone know what's a buffer system that's used inside the cell? Something there's actually quite a bit of around in there. It's phosphates. So it's a phosphate-based buffer system that's used inside most cells, I should say. Okay. And so they're just showing here some of the examples that are used. That first one, that's just acetic acid and acetate from organic chemistry. Then we have the bicarbonate system and the phosphate system. Okay. So now let's look. This one is a little different. We're going to use the Henderson-Hasselbalch equation to determine the pH whenever we're mixing some of the buffered solutions together. So we mix some of the acid, we mix some of the base, and we just see like what happens. Okay, and so this is using a phosphate system. And so I actually, well, let me just look at my cheat sheet here because it tells you, because on here it's not, the phosphate system. It's utilizing the same numbers that we had in the first example when it was 0.063 to 0.100. Then it adds an acid, and remember that was at pH 7.00. Technically it was 6.9994 or something like that, but roughly 7.00. So you're going to add in some acid. Now, whenever I taught Gen Chem 2, I would do what I call the ice table. This is a little similar to this, but a little different, just because it was easy for me to remember ice. It just made perfect sense, and so I'm going to show that example in just a moment. Okay. Is that them doing this construction of some sort out there?
I think it's thunder.
Is it really thunder? Because the echo is really funny through here. And so, just lovely. My roof is still not fixed, and so we don't want it to rain anymore. All right, so let's go ahead and work this out. So, what I like to always do is I write, we're adding acid, which it doesn't really matter. Does the acid react with A minus, or will it react with the HA? The A minus, so it doesn't really matter. Once again, the chloride anion we're not going to worry about. And whenever the H reacts with A minus, it becomes HA. Does that make sense? Okay. Sometimes that's the hardest part, making sure which is, because if you add base, it reacts with HA to make A minus. And so you just don't want to mix that all up. Okay. Then we create what I call the ice table once again. That's for initial, the change, and equilibrium. I think the previous table, the one that they show in the PowerPoint, which I can't change because it's a picture, is just initial and equilibrium. But sometimes people make mistakes. Okay. Now this time the volume is changing. So we're going to have to convert between moles and molarity and things like that. Well, we already know the initial moles of the A minus and the HA from that first problem. Okay, so that was 0.063 of the, oh, whoops, I misspoke. It's not the exact same one from before. I'm sorry. They give it to the same thing, but it actually ends up, the HA form is the 0.63 that's given in the, so 0.063. Okay, and then the other one, the one that has, you know what? Is there? Let me just double check something. H2PO4. I think there may be a typo on that original table that they put in here. So here, let me just erase that. Now we all already know that the, oh, that's not the eraser. Well, let's just, no, well, okay, I'm going to write the same thing down, but that way I can do it again. So we had HCl being added to A minus, going to make HA. The equation, what it says, and then still initial, change, and equilibrium. What was given in here is it said that there was 1 milliliter, which if you don't mind, I'm going to go ahead and convert everything to liters. 1 milliliter is the same thing as 0.001 liters of HCl, and the concentration of the HCl was 0.1 molar. Remember, a molar, what is it really in units with moles per liter, right? So that'd be the same thing as moles per liter. Once again, that's HCl. So we need to figure out how many moles that is of HCl for our initial. So that's really simple. If you take, for example, 0.001 liters, and we times that by 0.1 moles per liter, see the liters canceled out, And we are left with 0.0001 moles of HCl. So that's the initial amount that I was adding here. 0.0001 moles of HCl. We're going to do the same thing for the A- form and the HA form. Okay. So I don't know if people had already printed this out, but my old eye is trying to look at the little table. I just don't like the little table. All right, so it says that we have a solution that contains 0.63 molar of Na2HPO4. Okay? So we've got to figure out how many moles of that and how many moles of the other thing. For the very first thing is we look at those two, and I'm just going to write out, these are the two things that they have. It says Na2HPO4 and NaH2PO4. Notice the sodium doesn't really matter. That's, if you remember, that's called a spectator ion from Gen Chem. And what is important is it tells us that we had 0.063 of this one. And we had, now I am going to erase this part from before, so that way. Of the NaH2, we had 0.1 molar. And there were 99 milliliters of each one of those. So once again, 99 milliliters is the same thing as 0.099 liters. I'm going to do that for the one in darker color since I forgot to change my colors. I'm going to do it first. So that's 0.100 moles per liter. I'm trying not to. And that one, that dark one that's down there, is that this one right here? Is this one the HA form or is that the A- form? That's the HA. Okay, and so the reason why I want to say that is it's just easier to call it HA than it is to keep writing that all out. So when we do this, this comes up to 0.0099 moles of HA. So that's going to go here. 0.0099 moles. Okay. Give everybody a moment to get caught up before I do my little erasing so I can do the next one. Okay, so I'm just going to erase. Oh, it's not going to let me erase that part. Of course not, because I paused it. It's one of the reasons why I like the other program better. All right, but that's easy enough to change. Let's see if I can. I don't think it's going to let me. Nope, let me just. Okay. So what we're going to do here, I'm going to change the colors, that way it's a little easier to see, for me at least, see the difference between the two. We're going to do the exact same thing, but we're going to do it with the A- form. And it was also it started off with 0.099 liters. I'm going to just put it over here for right now, 0.099 liters. And it was 0.063 moles per liter. And so you're going to do that, the math there, which that one I definitely don't have. It's going to be very similar to what it started off with. I mean, well, you'll see in just one what I mean. And I get for its number, and I'm just going to write the answer that I got right up here. 0.0624, okay? and it's moles. Okay, so now that being said, we looked at all of the initial concentrations. Now this is the change. So this isn't as difficult as what some people may think, because it's the stuff on the left-hand side from where we have that's reacting to make stuff on the right-hand side. So all you do is you look to see which one of those is a smaller number. Which is smaller, the one for the moles of HCl, the moles of A minus? HCl, because the A minus only has 2 zeros and the HCl has 3 zeros. So, and it's disappearing, right? We're going to use that. So the reaction is going to occur until you use up all of the HCl. Well, for every HCl that reacts, it's that same number of A minus that's going to be disappearing, and it's exactly that same number of HA that is appearing. So it's a plus over in here, 0.0001. And technically these are all moles. Let me see if it'll let me erase this. Oh, good. It will, so that way it doesn't. Okay. Which one's the A minus? So if you look down there at the one on the bottom right hand, it's going to be the one that has the fewer number of hydrogens. HA has
Na2HB.
yes. Mm-hmm. Now we just do the math from the initial to change. So therefore 0.0001 minus 0.001 is 0, which makes sense because it's going to react until the strong acid is gone. Okay, and we're going to subtract the 0.0001 from the other one, and you're going to get was 0.00623 moles of A minus. Right? Because it's going to be disappearing. Because for every mole of HCl, 1 mole of the A minus will be disappearing. Oh, yeah, sorry. Yeah, I just read it wrong. Good catch. Good eye, good eye. In fact, it's correctly on my calculator. I don't know why it said it wrong. Okay, 00614. Good eye. I'm just checking to see if you're awake.
Right.
Good job. Good job, you are. And let me change the color back. So that way, this one, hopefully I did this math correct. 0.01, right? Because if you add one more to that, yes. All right, moles of the HA. Let me see if it'll let me. Which one's which? Oh, good. Well, let me slide it up. Okay, good. All right. Let me just make sure real quick. HA is on the last one. So I'm going to rewrite the Henderson-Hasselbalch. Once again, more for my benefit than yours. You're looking at it in your notes. The pKa was given in the original one. It's 7.2. So unless you're asked to determine it, I would always give you the pKa. If I give you the pH, then chances are you're going to be looking for the pKa. Plus the log of the base form. Okay. And if you, just in case, you're like me and I was like, oh, I can't remember what the base form is. Oh, don't do that for me. The base form is the one that ends in a 6 or has a 6 in it. The acid form is this one. Then we do our good friend plug and chug. 7.2 plus the log base 10. Once again, 0.00614. Divide that by 0.01 in parentheses. And if I go to just 3 significant figures here, it's going to be 6.99. So then let's just check to see if this makes sense. We added acid, and we actually added a strong acid. The pH went down, so it should. But notice it didn't go down by very much. And the reason why is because that's a buffer system. The Henderson-Hasselbalch lets you figure out the buffered system. And so that's why your body utilizes this to help keep the pH of your blood at homeostatic levels. The cells utilize this. We utilize this in the lab whenever you're doing chemical reactions or you want to grow bacteria or whatever, do protein expressions. These are just things that are very important to keep in mind, and it's very useful. All right, so the buffer, you need to always pay attention to the pKa. Because remember, this is by a log, this is log base 10. So 1 pH unit away from it is actually a 10-fold difference. Okay, 2 pH units away is a 100-fold difference. So typically we say the buffer is most effective within 2 pH units to the pKa. And we always look at it with respect to the acid and not the base, because otherwise it would just get even more confusing trying to remember pKa's versus pKb's and everything. So you always do everything in terms of pKa's. Right. So that's why it says within plus or minus, that's what you're within 90 to 110% of whatever you started off with. That's the blank one I couldn't get rid of. All right. So this here is just showing you the buffers of the cells being phosphate. Once again, as we mentioned, the bicarbonates, and the carbonates is the buffer for the pH in the blood. And we can see here, this is called the Bohr Effect, that you can change your pH with respect to whether you're hyperventilating or hypoventilating. And you have to start thinking about Le Chatelier's principle. Remember, Le Chatelier's principle is whenever things are at equilibrium, if you perturb that equilibrium, it's going to shift one way or the other to try to regain that equilibrium. And so,
What was the name of that?
Le Chatelier. Let's see, I think I can spell it, but okay. But it's just that the whole idea, if something is even though it may look like it's equilibrium and it's static, it's really a dynamic process. Because if you take away one side, this side's going to decrease in order to make this side have bigger, or vice versa. If you add to one side, it's going to go down, so the other side will go up. So it's kind of like the teeter-totter idea.
So that is like the equilibrium?
It has to do with equilibrium. So if you start taking product away, it's going to make more product. If you add more substrate in, it's going to make more product. Or if you take substrate away, it's going to make more, go backwards and things like that. Because these are equilibriums. They go both frontwards and backwards. Let me erase good old Chatelier. So medically speaking, this is relevant. If we just look at carbon dioxide, that's what we're exhaling eventually. But before we can exhale it, it's in your blood in liquid form. It's going to react with water to make bicarbonate. Bicarbonate then is actually an acid which dissociates to H plus and HCl, and then the bicarbonate anion. Okay, so what this means is if you hyperventilate, you can actually increase the pH of your blood. Sometimes people get this backwards. So what we mean, if you think about it, if you're hyperventilating, what does that mean? You can't breathe, you're not catching breath. So that means more carbon dioxide is leaving your body than oxygen coming in. Since the carbon dioxide is leaving your body up here, that means it's going to go this direction. By going this direction, you're decreasing the H+. And remember, decreasing the H+ increases pH because it's an inverse relationship. Just like if it's hypoventilation, so you calm down, you're going to decrease your blood pH. Okay, because you're going to get more oxygen, less carbon dioxide, so it's going to go the opposite direction in order. I mean, it's going to go the opposite direction. I drew the same direction. It's going the opposite direction, and so therefore the amount of hydrogen that's loose in your body is going to increase, and by that, then the pH is going to go down. Okay, and so. There's some things to keep in mind whenever you're looking at trying to do a buffer. One of the very first things is you got to look at the pKa. Obviously, if you're looking at an acidic system, you're not going to choose a pA that has a really high pKa. Choose a buffer that has a really high pKa. You need to look at to make sure it's suitable ionic strength. If you have to add too much salt to it, that's bad. Make sure it's soluble, because not all buffers are as soluble as others. And of course, it should make sense that you don't want it to interfere with your biological systems that you're working with. Okay, so that's why a lot of this. These are just some examples that are used. They usually have really, really long names, and then they give them nicknames. So the one at the top, some people call it heaps, some call it heapies, rather than saying, N2 hydroxyethylpyridine, N2 ethane sulfonate. And then there's mops and pipes, and there's one called caps and tris and things like that. And so that's why it's just much easier to call them by their nicknames than their really long names. And then those are the given pKa's. And so that makes sense. All three of these have pKa's roughly right around neutral, roughly around that which is biologically relevant. Okay, I just want to briefly talk about osmotic pressure. And it's really related to the idea that it's a lot like the ideal gas law, P inert. You think back to PV is equal to nRT. It's the same principle, except here they're looking at osmotic pressure instead of gas pressure, right? And so this just shows you the fact that our cells have semi-permeable membranes by default, and so therefore if you change the osmolality, change the concentration of ions one way or the other, you're going to change the volume of your cell. So this is the easiest way to think about it. Isotonic, iso means equal, so there's no net movement. That's why whenever you give blood or anything like that, they're going to make sure that the pH of the solutions they're putting it in or whatever that they're messing with is not going to be one way or the other. The salt and everything's going to be the same. If it's hypertonic solution, then the water is going to move out. Okay, so when the water moves out, the cell is going to become it's called crenated. Not cremated, crenated, because it's going to collapse on itself. If it's hypotonic, the water comes in and the cell can burst. So it's really important, even in vivo, that your body keeps this well regulated. But that's just a little side point. Then on your own, I just want you to review. We've actually discussed this a little bit with ions and polar and nonpolar, but you want to make sure that you understand it in better detail.
So next class we